Hello, everyone. My name is Alain, as was mentioned, and I'm going to present our work with Julio and Alvaro. And to put you into context here, we're going to talk about a little bit about deep learning and its successes over the last decade. There's been a lot of like miracles, like we could say, great advances in image recognition and language modeling, etc. But most of these advances have come from the fact that we have tried lots of different architectures. We've tried convolutional networks, we've tried recurrent neural networks, and even lately transformers, and we have great successes, but not so much has been done in trying to try different ways of training our models. So we have stuck with the idea of just throwing random sets of data to our models and hoping that they learn. And this does not make that much sense to me. It's like we trained our child from preschool to somehow be able to solve addition and differential equations at the same time, over and over again, until they get it when they graduate. So that doesn't make much sense. So a notable exception to this trend is something called curriculum learning. If you haven't heard of it, it's just a very simple idea, and the idea is to just show your models the easiest examples first, and then progressively show it harder examples. So they learn like we do, like from easy to difficult. And the problem is, of course, and it has shown great benefits. We know that it produces more robust results, and learning is more efficient. And even sometimes it makes learning possible. For instance, if you've heard of the AlphaStar model that is able to play StarCraft 2, the first iteration of training depends on imitation learning, and then it is let out to train on its own and learn how to play. So the problem is, why aren't we using curriculum learning all the time? If it's so good and so great and so awesome, sometimes it's not so easy to tell what is easy and what is hard, right? And if you look at these images, could you tell me which is the hardest and which one's the easiest? I wouldn't be able to tell you. So work has been done to try and solve this problem. And one of the solutions is something called a Zscore, a consistency score for images. And the basic idea of this is simply to try and assign a score to an image based on the ratio of models that would be able to learn that image in a given setting. So if you have a Z-score of 1, it would mean that all models were able to learn that image in this case, or sample. A Z-score of 0 means that that image was really difficult because no models were able to learn it. And the great thing, I mean, why aren't we using this then? If we have solved this problem with this Z-scores, because it is computationally unfeasible to get reasonable estimates or accurate estimates of the Z-score requires training thousands and thousands of models. So it has been done for certain data sets, but it's prohibitively expensive to apply to a different data set. So that is where we come in. We thought, could we learn a model that actually solves this by using deep learning? I'm sorry to say, we use deep learning. And if we can learn this difficulty, these Z-scores, can we actually apply them to different data sets and actually get to this problem? And that is basically what we try to do in our work. And we tried in 3 different methods. Regression, standard regression. Very simple. We try to actually predict the scores, but then we try progressively simpler alternatives because maybe this is too difficult to learn. So our second approach will be Bayesian personalized ranking, and if you haven't heard of it, it's just a way of trying to learn, to get our models to learn a way to score our samples in a way that is consistent with the ordering we want to induce. So what we actually do is just compare 2 images and try to train the model to guess which one has the highest score, and that's it. It's very simple. And finally, if we can't even do that, we at least want our models to be able to say, okay, don't tell me what the actual Z-score is, but just put it on a range. We will just bin it, and we'll put it on a range, and hopefully you can do that. And we tried that. And we tried it in 2 different settings. One is an in-distribution setting, which is where we train our models, which is Cypher 100, a very standard image data set if you don't know about it. And we also we evaluated out of distribution on Cypher 10. We train our models in Cypher 100, and we evaluate them also in Cypher 10, so we can see if they actually can be used to predict in data sets they haven't actually seen. We train them with the smallest are just resonance 18s with 10 different seeds. And what we find, and what those graphs are trying to tell you, is that these models are really bad. The yellow line is the in-distribution score, which basically tells us that we can only get about 14% over the random baseline, which is really, really bad when we're actually trained on that data set. And when we evaluate out of distribution, our models devolve almost to random guessing. So for our 3 approaches, we find that these results hold. And this suggests a very specific truth that maybe it's not so easy to predict these scores from image features alone. So we thought also maybe these models are not really good at predicting specific scores, but maybe they can show a trend, and maybe they can induce an ordering that's still useful for curriculum learning. And that is what we actually tried next, and we evaluated them using the Spearman rank correlation, which is simply a score that tells us how similar are 2 orderings of numbers, not taking into account their values, but just their orderings. And what we find is that our method of BPR shows the greatest performance. It actually shows decent correlation on the in-distribution setting, but we find that when we go to out of distribution, the strength of the correlation drops significantly. And basically what this is telling us is that the features of the images alone is not sufficient to predict what the difficulty of an image is. So there's something else. And that is what we're currently working on. We know that image features alone can't predict difficulty, and this is difficulty from the point of a machine learning model, by the way, not from the point of us humans. And it also tells us that it's not so easy to say that an actual image is difficult per se. It's that, or a sample per se is difficult, but that its relation to the other elements from a data set determine how difficult an image is. So what we're trying to do in future work is trying to find scores or metrics that align show how a single image relates to other images, to try and see if it helps us predict these things. And also we want to do other things. We want to train these things on ImageNet, because a possible drawback of this is that maybe we're not learning features that are good enough to extrapolate. But we have done some testing on ImageNet, and the results are currently holding. So we're going to wait on that. And also we want to train with different architectures just to make sure that it's not that resonance aren't good enough to just solve this problem. And also we want to see, even if these models aren't so good at predicting these orderings, we want to just check if they actually create decent curricula anyway. And that's it. Thank you very much for your time.